Hey everyone, welcome back. This is section 2.2, differentiability. Much shorter section than 2.1. In this one, we're going to determine where a function is not differentiable. And it's not differentiable at four places. It's not differentiable at a corner, a cusp, a discontinuity, and a vertical tangent. And in a second, I'll show you what all those mean. And then we're going to approximate these things numerically and graphically. Okay? This means we're going to use a calculator. We're going to use a calculator to find a derivative. Last time we talked about how to use a calculator to find the slope at a point, or the derivative at a point. Today we're going to use the calculator to show us what a derivative graph looks like. To be differentiable, a function must be continuous and smooth. Derivatives will fail to exist at 4 points. At a corner, which is like absolute value. That's where two lines meet and then change. At a cusp, that's like x to the 2/3 power. A cusp and a corner are very similar, but a corner is lines and a cusp is curves. And a vertical tangent. Why is there no slope right there? Because that slope is so steep that for one instant it's actually vertical. It's undefined. And a discontinuity. This is one example of a discontinuity. This is called a jump. There's also an asymptote, and there's also a hole. So, another example would be an asymptote. Another example would be a hole. Okay? Any sort of discontinuity, or a place in the graph where the graph doesn't exist. Question. Is a corner continuous? Yes, a corner is continuous because you can draw it without picking up your pencil. Is a cusp continuous? Yes, you can draw it without picking up your pencil. Is a vertical tangent continuous? Yes, you can draw it without picking up your pencil. These three are places where the graph is continuous, but not differentiable. Most everything we study in calculus will be differentiable. Very few things have corners, cusps, and vertical tangents. However, they do come up maybe once or twice in the AP test, so we just have to be aware of it. How do I do it on the calculator? Well, there's two ways. And you need to know at least this one. This one is the one we talked about in section 2.1. It is very important that you know how to do that. This one, I'm kind of about. I'll show you how to do it, but I don't do it in class. It's not really necessary. Remember that half the test is no calculator. This is extremely important for that part of the test. This, not so much. Let's use nderiv to see the graph. This one isn't as important. But this method is when we want to see the entire graph so we can guess at what the derivative is. We go to y equals, we hit math, and we go down to nderiv. We type in the function, x, I don't know why, and then hit the graph. That's the graph of the derivative. So we can see what the derivative is there. Okay? We'll do a practice problem like this in a second. To find the derivative at a specific point is what we said last time. It's second trace 6. That will actually give you the specific number. Okay, let's take a look at an example problem. If I want to find the derivative of this thing, I would have to do the limit as h approaches 0 of ... You guys know how to do that. It would take a little while. So let's use our calculator. I want to find the derivative at 2. Let's do the easy way first. X cubed, second trace 6 is derivative. There's the original graph of x cubed. I wanted it 2. And I get 12.000000001. Be smart. The derivative is 12. I don't care about this. It's an estimation. It's a rounding error. Calculator makes mistakes. So that's the most common way. This is the second trace 6 way. And it's the way that I'm going to do in class. But let's do the other way so you've at least seen it once. Go to y equals, math, down to nderiv, which I think is number 8. Yeah, it's nderiv. I want the derivative of x cubed, comma, x, I don't know why, and now I graph it. What this is graphing is the derivative graph. So, this graph from nderiv, this is the derivative graph. This is the graph of y prime. And what's it kind of look like? It's a parabola. It's something with an x squared. Oh, look, the derivative of an x cubed is an x squared. But that doesn't tell me the slope at 2. That just tells me the entire derivative. What if I want to find the point at 2? Second trace. I'm not going to do the derivative now because I already have the derivative. So I just want the value at 2. Oh, look, it's 12. We already knew that. And again, get rid of these because it's just an approximation. So I will do this method almost every single time. In fact, I hardly ever, if at all, use this method. But now you've at least seen it. Okay? The calculator may return an incorrect value if you evaluate a derivative at a point where it's not differentiable. Let's take a look at f equals absolute value of x. So, absolute value of x. Before I do this, what is the derivative right there? Well, what is that point? It's a corner. There is no derivative at the corner. This should be undefined. It should tell me undefined. Second trace 6 at 0. It tells me that the slope is 0. The slope at x equals 0 is not 0. Even though it tells me that. Why not? Because x equals 0 is a corner. So the derivative does not exist. Be aware of that. The calculator just guesses. Be smarter than the calculator. Know what's going on. Okay? Differentiability implies continuity. If there is a derivative, then it's continuous. But it's not true the other way around. If there is a derivative, then it's continuous. But just because it's continuous doesn't mean it's a derivative. Why? There's 3 points that prove this wrong. What 3 points are continuous but not differentiable? Corners, cusps, vertical tangents. So if it tells you it's differentiable, it's continuous. But just because it's continuous doesn't mean it's differentiable. Okay, here's a review. Most of the functions we see are differentiable, meaning that they do not have corners, no cusps, no vertical tangents, or no points of discontinuity. The graph will be unbroken and smooth with a well-defined slope. Most of the problems we do are like that. Polynomials, rationals, trig functions, exponential functions, logarithmic functions. In other words, pretty much everything we do are all differentiable. They're all smooth and continuous. Key thing for today, remember corners, cusps, vertical tangents do not have derivatives. Also, if the graph is undefined, if there's a jump, a hole, or an asymptote, it doesn't have a derivative either because it's not continuous. If it's differentiable, it's continuous, but just because it's continuous doesn't mean it's differentiable. As always, if you have any questions, come see me. Thanks, guys.